Katie, we'll start when you're ready.
All right. Good evening, everyone. Welcome to yet another webinar. And a warm welcome to all our participants joining us today across the SADC region, of course, and beyond. My name is Getty Shinda, and it is my pleasure to welcome you today to the Young Professionals Program webinar titled Tackling Hydrogeological Realities, Low Yields, Poor Quality, and Complex Systems. This webinar is organized under the SADC Groundwater Management Institute Young Professionals Program, a platform dedicated to empowering and connecting with the next generation of groundwater professionals in our region. As we all know, groundwater is a vital source for water for many communities, industries, as well as ecosystems. Yet, its sustainable development is often constrained by difficult hydrogeological realities, such as low-yielding aquifers, deteriorating groundwater quality, complex geological systems, which can sometimes limit water availability. Increase in development costs is another challenge, and which sometimes undermines the long-term reliability of groundwater supplies. This webinar brings together practitioners, researchers, and of course, young professionals to examine these challenges, share practical experiences, and explore innovative, science-based approaches for improving groundwater assessment, development, management, and protection. Before we begin, I'd like to acknowledge and thank the SADC Groundwater Management Institute and the entire team that is behind the scenes. And then, of course, our speakers. We have 3 amazing speakers lined up for today. And like I always say, this webinars cannot happen with our young professionals. So thank you very much to our young professionals, as well as our partners and participants that are joining us today. We truly appreciate your time and choosing to join us this evening. So before we start, I'd like to just make a few housekeeping announcements. The first one is that keep your microphone muted unless you are requested to speak. And also, I encourage the participants to use the chat box for comments or questions or any sort of engagement while the presentations are continuing. At the end, we will have a Q&A session, a dedicated Q&A session, where our participants will be given an opportunity to ask their questions. I'll also put in a registration link in the chat, and we can have all our participants register with that link. All right. With that shared, I will then move into just briefly going through our agenda that has been shared by Tokozani on our screen there. So we are really honored and fortunate to have an excellent lineup of speakers today. I'm sure there are no strangers to the majority of you. First, we have Prof. Kawawa, who is actually our keynote speaker today. And his presentation will answer the question, can saline groundwater be freshened? New insights from the Machile-Zambezi River Basin. His presentation will be followed by Dr. Josephina Hamutoko, and her presentation is titled The Use of Isotope Hydrology in Understanding Hydrogeological Processes, with a case study from the SADC region. Last but not least is our very own young professional, Ms. Diana Nehale, whose presentation is titled Water Quality Assessment and Monitoring in a Karst Aquifer Affected by Mining Operations. This is a case study of Chudi groundwater aquifer in Namibia. So that is what we have lined up for today. And I know why you guys are all on the call, so I do not want to waste any more of your precious time. So I will now introduce our keynote speaker for this evening, Prof. Kawawa Banda. Prof is an associate professor in water resources management at the University of Zambia. In 2025, he was appointed as the Oliver Tambo Research Chair in Water Conservation, focusing on interbasin water transfer potential between the Luapula and Zambezi Basin. He is also the leader of the Integrated Water Resource Management Center, a center of excellence leading research on water resources management. He has a Bachelor of Science degree in geology, a master's in integrated water resource management, and a PhD in environmental engineering with a strong focus on groundwater and surface water applications. He is involved in various international and local initiatives to support research and training on water resources in the SADC region. His research interests are in remote sensing technology and its applications, water accounting, hydrological modeling, and environmental geology. As part of community service, he is the network manager for the Africa Groundwater Network and chairperson of the SASCAL Graduate Program, Academic and Scientific Committee, hosted at the Namibia University of Science and Technology. Today, he will answer the question, can saline groundwater be freshened? Ladies and gentlemen, help me. Please join me in welcoming Prof. Kawawa.
Much for that beautiful presentation and welcome. I'm delighted to be part of this session today, this webinar, and thank you to SADC-GMI really for facilitating this. Let me just share my slide. Let me put it in PowerPoint. Okay, thank you very much. Keto, can you confirm you can see my screen?
Yes, I confirm I see it. You can proceed, Prof.
Thank you. Thank you very much. So this evening I'll be talking about saline groundwater and whether it can be freshened, and really drawing from experiences around the Machile-Zambezi River Basin. I want to start by highlighting that, of course, this work is being done in a collaborative manner. And of course, SADC-GMI is one of our partners in as far as implementation of this program. Now, quickly, all of us, if by now you don't know, groundwater represents the largest source of fresh water. This is obviously very important for regions where scarcity is a big issue. Semi-arid regions to arid regions are obviously the most impacted when it comes to issues of water availability. Unfortunately, it's not only about water availability. What we do see now is that we've also got issues to do with the quality of the water itself, in as far as this resource is concerned. Now, groundwater salinity has obviously come to become an important issue from a perspective that over 1 billion people actually are impacted or are affected by issues to do with groundwater salinity. Now, some of you may not know what salinity is. Okay, so salinity is really, increased concentrations with regards to, normally it's due to sodium and chloride concentrations being elevated. It threatens the availability of renewable fresh water in some regions, but also there's a threat that it can cause increased contamination, particularly where you've got access to the sea. That seems to be a very, very big issue when it comes to groundwater salinity. Now, I'll really focus on a case study where this salinity is really hosted inland. Okay, meaning there's no access to any sea that is bringing in this salinity. So it's in the middle of Africa, but with high salinity conditions occurring. And this is in the Machile-Zambezi basin. I'll show exactly where this area sits. But you can see from the picture, this man here is literally drinking water that is just harvested from a nearby stream because he's got no access to good quality water, as it were. Now, if you read the SDGs, access to good quality water is really a fundamental human right in that regard. So to understanding the mechanisms, the processes that really affect, groundwater salinity is something which is important in as far as it will provide insights, in as far as understanding what type of groundwater management interventions you can really put to preserve and protect this resource. Now, let me highlight a big picture perspective, okay? One of the biggest disasters at the moment that we're facing is issues to do with climate change. Now, this is the picture I show here of Southern Africa and the threats that exist in as far as climate exists. Now, you can see there's a lot of red across Southern Africa. And from all the models, okay, what we do see in them is that our future will be much warmer. Our future will have less rainfall in that regard. But the distribution of this risk is really across the entire Southern Africa. Okay, that's what our models are really pointing in that regard. When you look very deeply into things like soil moisture, which are important in as far as recharge is concerned, the picture is really the same. Okay. Now, we've also done some local scale type of studies to really unpack how this would look like in as far as basic calculations, your water balance. Okay, if you think about all the water that falls from rainfall, take out the evaporation, do you see a drastic reduction in as far as the future is concerned? Okay, and for some of the areas, particularly within Southern Africa, in the Machile-Zambezi basin, we see up to 30-40% reduction in as far as recharge or at least rainfall amounts is concerned, pointing to the fact that recharge itself would be a big issue in some of these particular systems as well. But does that have any effect in as far as salinity is concerned, in as far as water quality is concerned? That's part of the issues that we were trying to investigate in this study. We did a hydrological model, okay? And for some of you who have not worked with hydrological models, what basically the hydrological model was trying to sort of investigate, will we have enough water or enough rainwater that is then recharging our aquifers, sort of also bringing in that freshening effect in the system. Now, where you see this sort of black outline line in the slide, that is where this Machile basin really sits. And you can see that in these regions, you'll be getting up to about 30-40% reduction in terms of how much recharge is going to go into this system. If you think about it from a projected climate future, scenario. Now, You might be wondering, in as far as this Machile-Zambezi Basin is concerned, where is it exactly? So the Machile-Zambezi Basin is in the southern, part of Zambia, but seated in the wider Kalahari Sand System. So it's right at the border between Zambia, Namibia, that area. So Caprivi region, just a bit north of that, region. That's where if you look at my figure, it's up there in as far as where it sits. Okay. Now, if you go there today, what you're going to notice is that life looks normal. There's vegetation, there are trees, but the groundwater is very, very saline. Okay, salinity as much as that of the sea. Okay, sea level salinity is about 25,000 microsiemens per centimeter. If you took any measurements in there, so very saline environment. We did an investigation to collect multiple type of data to understand how does the geology look like that could be facilitating this salinity. So we took it from the northern regions going down into Botswana, Namibia, the neighboring countries to see how is the variability in the Kalahari system in as far as the geology is concerned in response to things like the resistivity values. Now you see a lot of red down there. Now the red are just telling you that you've got high resistivity type of zones. High resistivity means that, there's a possibility of fresh water sitting there. But the minute it drops down to less than 3 ohm meters, it means that the risk of salinity is very, very high. So the distribution varies, okay, from the north to the south. Okay, this distribution is important in as far as what is the complexity associated with this particular system. Okay, so what exactly then is the problem? Okay, so the issue here is that you've got a threatening climate change problem. This climate change problem is telling us that you're going to get reduced amount of recharge. Okay. Now you've also got a challenge in as far as the occurrence of this system that has got these high levels of salinity. But why doesn't it get diluted? Okay. Why does this salinity persist in as far as this environment is concerned? Because you've got people who are living there who want to get access to fresh, water in that regard. So that's sort of the scientific problem that, we're investigating this system. Now, because of time, I'll just highlight key issues in as far as, the results or findings are. So we set out first to drill a relatively deep borehole in this area. Now, because of the nature of the geology, it's a bit complex to drill, given unconsolidated formations, difficult to collect cores. Okay, so we had to fabricate a special type of tool to collect, the data itself. And what we see is that, most of that, salinity is leaching out from, rock. Solid, concentrations of halite, and there's also some gypsum. That is, so we could see evidence that, look, in as far as the salinity is concerned, the source is probably leaching out, but it was sitting in a very thick, distribution of clays. And clays has got very low porosity. Okay, it's got high porosity but low permeability in as far as its characteristics in that regard. So what if you've got this type of salt in this system? Well, we thought, okay, if we know the distribution of this system, okay, maybe we can intersect places where you just get predominantly fresh water sitting. Maybe let's do a hydrocensus where we collect samples across the basin and then identify where you've got high, EC, where you've got low EC. Maybe that will help us plan. And we realized that, look, actually, the concentration of this salt was centered in a more central region. So this center, where you see these big bubbles, okay, that's where you get most of the concentration sitting. But as you move away from this region, we realize, wait a minute, you're actually getting fresh water into the system. But if you look at, again, the topography, Okay, in the fringes of this system, that's where you've got the high lying areas, but in this, and then the central regions is low, meaning that from a topographic perspective, okay, and from first principles, your groundwater is moving from the high elevation areas into the low, lying areas. But why is it not getting freshened out when this water comes into this, system? So we decided, let us do a geophysical profile across, just to understand, first of all, the geology that is sitting in this area, and also the distribution of the salinity in particular area. Now, on top, you've got the west-east, meaning it was cutting west-east and then north-south across the system. Everything that you see in blue, that is that central region where the high salinity is actually sitting. We learned that it is sitting in really a clay zone, but you've got these lenses of fresh water coming about. Okay, and then obviously as you go up north and on the fringes, it sort of is sitting into a graben structure. Okay, so there's some structural control in as far as how it was formed in this particular system. So we decided to do a model. Okay, so basically a groundwater flow model. Now, what that groundwater flow model was simulating, okay, when you've got this fresh water coming from the north, south direction, right? So coming into this saline zone, it sort of hits this impermeable system where the clay is sitting, and then forms a spring. Okay, because it's got nowhere to go. So it needs to push up through that particular system. It's lost to evaporation, but then the saline pool remains as it is. So the saline pool had relatively concentrated levels, or at least high levels of old water, because there was no freshening coming in, whilst, the fringes of this system had then more permeable, type of systems in that particular regard. So we've got a situation of basically a salt swimming pool, if you like, okay? And it's got no way of, being diluted because there's no new water coming into this system. Okay, that's what the model basically showed us, okay? But we thought, look, we still need water in this system. So where do we get water? So we investigated the nearby Zambezi River and said, what about the important surface water, groundwater interactions? What can we learn from that? Do we have enough water that is just sort of being discharged from the Zambezi, okay, into the surrounding area? And how far does that particular, system go? What we learned actually was interesting. We basically did a conjunctive model where we combined SEWAT, those who've worked with, salt systems. So it's a SEWAT model and sort of the hydrological system in that area. We learned that within close proximity, at least up to 5 kilometers, the Zambezi was strong enough pushing this water inland. And because of density, dynamics, the fresh water is lighter, so it will sit on top. Then the saline water will go at the bottom. Okay, that was an important finding because the communities around that particular area then could tap into that, freshening water system that was coming from the Zambezi. But of course, with the risk that when you've got very low water levels, it means that you're now going to get this salinity now sort of propagating, a bit more. So through another project with which we are still doing, okay, we thought maybe let us now look into deep sitting systems. So to use a new approach called SEM, and the innovation with this method is that you're using drones, okay, to collect the receiver perspective of what your ground-based geophysics are doing. Okay, so when you run your geophysics, you've got a drone flying over this system that is collecting the data, and then on the ground, you're transmitting the signal into the ground. So what is the innovation there? Well, because you've got very, very high galvanic contact with the transmitter on the ground, you can then go deeper beneath this particular salt system that was attenuating the signal when you use other methods that are traditionally being used. Okay, so this is part of the campaign that was done. This was also done in Namibia. I think Dr. Josephina was involved in this. And what basically was done, you can see some of the apparatus and nice technology being used. We then were able to simulate an outcome that looks like this. Okay, these are just some preliminary results. And what we do see is that everything that you see in red on top, the shallow part of this system, okay, is basically this clay system, which has got low resistivities, which means it is quite saline. But as you go down, okay, as you go further down, you have these lenses of high resistivity, which we're not able to see from before. Okay, so the new technology has helped us to then map this, fresh, sitting type of, geology, if you like, within very, very saline conditions, as it were. I think that's a very positive thing, opening up opportunities for exploration with deep drilling. Unfortunately, these should go about 300 meters in the ground. Traditionally, we've been drilling, at least in Zambia, between 50 to 100 meters in as far as the drilling is concerned. We've got interesting hypotheses. This is still ongoing work. I'll not bore you with that information. We've also developed a kind of a profile in as far as our interpretation of what this new geophysics is telling us, okay, which is leaving me with key messages to conclude my presentation. That in these, saline systems, okay, this is something which is, of course, not unique to Zambia. We've got this Kalahari system that is extending into Namibia, Botswana, going down into parts of South Africa. What we see is that the shallow groundwater system seems to be quite well understood. Okay, what we're still missing in understanding is the deep sitting system, and we need new technologies to unlock this understanding. We see that there is a very strong concentration of salinity in the middle of Africa. You might ask, where is that actually coming from? Well, it's connected to a geological process. I don't have time to explain that, but if you have questions, I can try. Okay, and then also what we know is that climate change will create this environment to propagate more areas that could then become more saline. Okay, because if the conditions are fresh, that you've got reduced recharge, you've got a geology that allows that you can concentrate your system, you are prone to now start having increased salinity. So the threat of climate change is not only around recharge, but also a change in quality in some of these aquifers. Can we dilute this system? It depends. Okay, where it sits in a saline, in a clay, low permeable system, you struggle to really dilute, that system. Also, lastly, we shouldn't forget the perspective of how surface systems can then bring in that perspective of important groundwater surface water interactions in as far as where you can actually be getting this freshwater system. Thank you very much. That's my last slide, Geto. Thank you.
Thank you very much, Prof, for your presentation. But no, the answer, that's not the answer I was looking for, but I'm going to park it and wait for the young professionals to ask you the question regarding that answer on whether the saline aquifers can really be made better for us to use the water. Very interesting, innovative approach that the team used to try and get more information, but hopefully soon we will be able to truly unpack saline aquifers and really be able to help, use that water, especially the fact that it covers such a large area of the country. But without diving into the questions, let's first move on to our next speaker, who is none other than Dr. Josephina Hamutoko, very well-known hydrogeologist. So Dr. Hamutoko is a senior lecturer in the Department of Geosciences at the University of Namibia. And she holds an honors degree in geology, a master's in environmental management, and a PhD in geology. She also serves as the president of the Namibian Hydrogeological Association. Her research focuses on understanding and sustainably managing groundwater resources in dry land environments, particularly the interaction between shallow aquifers, surface water, climate change, and human activities. Dr. Hamutoko has secured numerous publications, scholarships, and research grants, both nationally and internationally. She is passionate about education, service, and inspiring the next generation of researchers. And we also know her as one of the youngest doctors, one of the young people to acquire the PhD. She has inspired many, many young people across the SADC region to go out and pursue their PhDs, myself included. So help me welcome Dr. Josephina. She will present the use of isotope hydrology in understanding hydrogeological processes with case studies from the SADC region. Dr. Hamutoko, the floor is yours.
Okay, thank you, Getty, for that wonderful introduction. And also thank you for the platform to share. I think I would prefer to switch my video off. So it's always a little bit challenging to talk after the professor, who is also one of my mentors, but I'll try to share some highlights of using isotope hydrology. So my presentation today is not going to focus on a specific case study and following the whole scientific process, but I would rather I would say I'm advocating for the use of isotope hydrology in the region, and I will try to show examples of how this isotope hydrology has been applied in the region to solve some issues, especially involving complex aquifer system. So this is the outline of my presentation. I will just look at techniques on how do we collect the data, and highlight a few case studies where we have seen success using isotopes, and then a summary and an outlook of what is it that we can do, what is it, our motivation in terms of doing using isotope hydrology. I think we cannot overemphasize the dependence of communities within the region on groundwater. Most of us, we really highly depend on that, especially in the rural communities where people are still not linked to the water supply pipelines and so most of them, they really depend on boreholes. And for us to even supply this water or to sustainably manage this, we really need a clear understanding of the hydrological processes that are governing these aquifers. Because imagine you have an aquifer, you are taking water from a well, and then you come back 2 days later, maybe there is no water, or 10 years down the line, there is no water in that. And that is a result of not understanding how the system is working. If you don't understand whether there will be recharge in that specific aquifer, the possibility of it drying up is very high. And so this is one of the reasons why we have to do this kind of studies, so we understand these processes. So one of the fastest growing technique used in understanding this groundwater system is the use of tracers. So tracers, you can use them for a lot of things. One of them being the groundwater flow patterns. You can understand recharge sources and mechanism. I've seen some people who have even gone to the extent of trying to calculate the recharge rates from tracers and groundwater mixing, as well as you can look at residence time. And one of the common traces that we use is isotopes. So really, when we look in the field of isotope hydrology, we are looking at the application of both stable and radioactive isotopes to investigate whether it's the origin, the movement, the age, recharge, quality of water within the hydrological cycle. So it's really has a wide range of application, stemming from, of course, depending on the question that you are trying to answer. So they are categorized into two. We have natural traces and we have artificial tracers. But in this regard, when we talk about natural tracers and artificial, or in this regard, we don't talk about the origin of how these traces got into the environment, but rather on the way that they were liberated. So natural traces represent traces that were present naturally in the environment, and they were incorporated in groundwater without the purpose of you wanting to study groundwater. While artificial tracers in this regard is those that have been deliberately introduced in groundwater to study the water movement. So for instance, if we look at CFCs have, when you look at them, they are anthropogenic. However, they have not been introduced with the purpose of studying groundwater. They are introduced by human beings in the atmosphere, but not for the purpose of groundwater. So that makes them natural tracers. And so, however, most of the artificial tracers, we use them mainly for small-scale, short-term studies. They are less effective in large aquifers because of the slow movement of groundwater. We all know that groundwater moves very slowly. So in that regard, then we prefer to use what we call environmental tracers because they occur naturally. They provide good insight, even in a very big, complex system, and taking into consideration both the spatial and temporal variation. So this is just an indicator of the different types of isotope. Of course, we have stable and radioactive, which is unstable. We have groups of different traces, and of course, they have different functions. So there are three categories of main application. One is tracing the origin of water. One is dating the age of water. And then the other important one is determining the identification of pollution sources. So how do we really collect isotope data? We follow standard water sampling procedure. Of course, if we are taking isotope value of water, but we can sample other sources like the soil water. So we sample soil and we are able to determine isotope from soil, and that follows another really long procedure. We can also sample trees for xylem and get isotope value. We can sample groundwater, surface water, rainfall. Generally, the sampling procedure is not so challenging, but it's very critical to follow it to the core. And also the storage of sample, the transportation, these are all important. One of the international partner in this regard is the International Atomic Energy Agency. They continuously support member states with training, with equipment, with expert mission, with sometimes sandwich programs that for countries to implement and also accelerate the use of isotope hydrology. So most of the countries that we have in the region, like in Namibia, they have basic equipment to analyze for stable isotopes that have been acquired through this agency. However, we still have limited capacity in the region on analyzing radionuclide, age dating, and so on. But they are there, it's just that they are still quite limited. So now moving on to the case study, I like to show this picture usually because I remember when I started doing my PhD looking at using of isotopes, when you search for the use of isotope in Namibia, it was really almost impossible. But now when you go even just on Google Scholar, when you search, you can say that almost every part of the country have been investigated with isotope one way or another. So that is good. It's showing that we are really using this technique. So these are just some examples of how isotopes have been used. One of the main function is determining the origin of groundwater. So in this case study, so this one, the first one we have done is in the Kuvelai, just in the Namibian side of the Kuvelai. And in this study, what we are trying to determine is whether the shallow aquifer and the deep aquifer were related. Are they getting the same, are they being recharged by the same events? And we were able to separate that in some region, which is in the ephemeral riverbed, there seems to be no connection between this aquifer, while if you look into pens and depression, there seems to be a connection, and this could easily be understood using isotopes. And then in another study, one of my colleagues, they were using they were collecting samples from trees and soil water to try also to determine where is the groundwater coming from. And they have done this in different areas in Namibia. So in Stampriet area, this is from Stampriet, then we have Waterberg and Tsumeb. So where they were able to make conclusion based on that. And then you can also use isotopes in groundwater surface interaction. So this example is from Southeast Botswana, where the colleagues, they have used isotopes to try to understand the interaction between surface water and groundwater. So the findings that they highlighted that there is really highly active groundwater recharge areas along the ephemeral riverbeds. So this is information that are quite difficult to get sometimes with other methods. And with this result, they were able to recommend sites in which we can target aquifer protection, because we know where the recharge area is, so we try to protect it to avoid contamination of groundwater. Then this is also just a highlight from the same paper of how stable isotopes have been used in determining the interaction between surface and groundwater. So for instance, using the first example in Northern Kalahari, they used stable isotopes, tritium and carbon-14, and through that, they were able to determine that the main recharge is coming through direct recharge through the soil profile. So meaning that if there is surface water and it can still penetrate into the ground, so it recharges the aquifer. We can also use isotopes for determining residence time. I think it's the only way we can determine residence time to get how old is the water. And in this study, the colleagues have looked at, this was also in the Kuvelai, they have used several tracers like carbon 14, chlorine 36, krypton 81, and helium to determine the age of the groundwater and also to provide some insight on the flow dynamics in Ohangwena 2. And they were able to conclude that it seems that recharge in that aquifer took place at least in the time where the temperatures were at least 3 to 4 degrees lower than it's currently today, meaning that the aquifer is getting limited recharge in the current times. So, which is an important implication for water resource supply. So, last case study is one of actually my favorite study, and if you are really looking at hydrochemistry and isotope, you should read this paper from Stadler. It was done in 2010 in Botswana, and they were able to use multiple isotopes and of course chemistry to improve the conceptual model for this. It's a sandstone aquifer, Kalahari aquifer. They were really able to analyze the flow regime, and they also determine the recharge conditions. And even in the same study, they were also able to identify pollution sources from the different isotopes. Like they used nitrogen isotope to determine the source of nitrate in that area. So in summary, there has really been an increase in understanding the groundwater resources in the region, whether we are talking about recharge mechanism, we are talking about flow dynamics, we are talking about interaction between different aquifers, we are talking about the residence time or sources of pollution, and even more so now there is a growing interest in using isotope in improving conceptual model, even to the extent of using them for calibration and validation. So this is really all to understand the process to promote the use of groundwater. So what is it that my outlook or my recommendations is that we need, of course, isotope cannot be used in isolation. It does not take away the use of classical methods when we are doing groundwater investigation. However, it's a very important tool that can be combined with these other techniques. And we are also pleading and encouraging member states to incorporate isotope into your monitoring network, whether it's rainfall, groundwater, surface water, and increase collaboration between the member state, but even between institutions in member state. And for those countries that have less contact with the agency, really try to work with the agency as much as possible. And hopefully we try and increase the technical capacity for the region, especially with regards to radionuclides and tritium and carbon 14. We have, I think, in South Africa, some labs that can analyze this, but it's really, really limited. So we need to increase this technical capacity for the whole region. So these are some of my references, and thank you.
Thank you very much, Doctor, for your presentation. It's always interesting I know you mentioned that a lot of progress when it comes to the interest on isotope has been increased over the years, but it's interesting how we know the terminologies, but we don't understand. Like isotope, many people fear just the term because not every person on the street knows what isotope is. Just the word isotope already, tells us that I don't want to focus on that. I don't want to. It sounds hard, but I really appreciate the way you gave your presentation. You really started from the basics, broke it down properly so that it's small bites and everybody can really understand that, at a broader picture, like these are the benefits when you apply these techniques. When you apply this technique, especially when you want to understand the origin of the water quality, the age, So it's a very, very important technique that we can apply as we conduct our assessment, groundwater assessment. So thank you very much, Doctor, for your presentation. We are now moving on to, we'll take the questions at the end. We'll now move on to our last presenter for this evening, who is a young professional, Ms. Diana Nehale. She holds a bachelor's degree in applied chemistry. She has over 6 years of experience as an analytical chemist in the Namibian mining industry. She is also a SADC-GMI young professional pursuing a SADC-GMI fully funded master's degree in environmental engineering, specializing in water through the Namibia University of Science and Technology. Her research focuses on groundwater quality assessment and monitoring of mining impacted karst aquifers to support sustainable groundwater management. She is a member of the Namibia Hydrogeological Association. Diana is passionate about advancing scientific research and strengthening water security and environmental sustainability across the SADC region. With that said, she will be presenting, her title is Water Quality Assessment and Monitoring in a Karst Aquifer Affected by Mining Operations, a case study of the Chudi groundwater aquifer in Namibia. Diana, the floor is yours.
Thank you so much, Katie. You put me with quite competitive people. I'm just like, but I'm like, oh, as a young professional, that's fine because I'm getting to learn from the best people.
No, you got this. You got this.
Okay, let me just share my PowerPoint. Are we able to see it?
I think it's still loading. It's still loading.
Yeah, it's coming through.
Mm-hmm.
It's on now.
Okay.
Yes, yes, you can proceed.
Thank you so much. Okay, so my study is still ongoing, and what I have to present today is based on historical data that we've been collected, and also a few findings that has recently been done. So why this research matters, why it aligns with the presentations that we're doing today. Namibia's water security hints on aquifers and mining city, right? There's a lot of mining that happens in Namibia, and most of Namibia's source is groundwater. Now, the specific study that I am conducting is around the Otavi mountain land, where we have towns, 3 towns specifically, Otavi, Tsumeb, Grootfontein, which is supplied by this Otavi mountain line karst aquifer system, and I'm going to focus on the 2D compartment karst aquifer. So the mining operations around the aquifer, there's been mining operations since 2014 to 2020, but due to there was a blasting that caused flooding into the open pit mine, and then there was closure. So during the 2014 to 2020, there was an operation, and then there's been a closure since 2020 until now. They've not started up with mining operations. So we get to study what the impact has been during operation and post operations after closure. So the challenges, what we are trying to find here is that, like we said, the karst aquifer system around there supplies water to farm, storage, lodge, and also non-water well fields, draw from the same aquifer that was mined from. And so we're trying to see, are there any mining impacts to the water system that this specific depend on. So on the study areas, that Otavi mountain land karst aquifer system is one of the most important groundwater resources in the central Namibia and contributes to supplying a substantial portion of the region's water. And it is a significant system hosted by fractured and karstified carbonate rocks, and the area indicates is also surrounded by mining known. There's the Sino mine, Dundee, previously known, and no, sorry, that's there's no aquifer, right? But the two main aquifers here that are known for is the Combat Aquifer and the 2D Aquifer. We also have Lake Guinness and Lake Ochikoto, which are also known to have some pathways linked to that. And so due to high permeable nature of the karst aquifer, the system provides a quite valuable resource to, and yet is also vulnerable to rapid changes in its quality and pathways. So the research questions that we're trying to answer here in the study is to know what is the interaction between the groundwater and the ore minerals, and what is the quality and quantity of the water in the aquifer, and what the hydrogeological state of the aquifer is. So the data that we have and are using for the study currently is we have the hydrochemistry data of the 10 sites that has been sampled during the mining operation time. So from ranging from October 2014 to September 2019, where they look at the major ions, trace metals, and the physical chemical parameters as well. So they also do the water level monitoring, a read of the boreholes in the mine proximity, nearby, and the pit as well. There's monthly monitoring for potable use water that they use for the mine, and also the surrounding farm boreholes, the surrounding boreholes around the mining area. Site rainfall is also recorded, and also the lithologies of the area has been there is data on that as well. So we're using the World Human Organization guideline, water guideline, and the Namibia water guideline as well, from the Department of Water Affairs in the Ministry of Water and Agriculture. So some of the findings that have been recorded are the sulfate that in borehole 7, which has had, okay, so there were sulfates conducted for about in the 10 boreholes, and most of the boreholes do not show significant concentrations of sulfates. They are all within the guideline, the water guideline, but we have borehole 5 and borehole 7 that indicated sulfates, and these are the boreholes that are in the proximity of the mining area around the pit as well. So with that, so we have sulfates of 1,505 being recorded as the highest for borehole 7, and this is due to the oxidative weathering of the chalcopyrite ore that is found in the area of the mining where they do the mining. And so when the chalcopyrite reacts with the water and oxygen, the sulfur components then are oxidized to sulfate and releasing acidity in the water, and they lower the groundwater's pH, which could then where there's been a record of 6.4 as a pH. So generally that borehole has been affected with sulfates oxidization due to the chalcopyrite sulfate. So this promotes quite a mobilization too, where potentially it could affect the groundwater quality of the karst aquifer. Then so yeah, so the aquifer is fighting back, to say. So we have the alkalinity remains low. It's the way where it's supposed to be buffering the borehole, but we have so the dolomite rock is neutralizing the acid, but the buffering capacity could progressively be depleted. So if the buffering system is exhausted, then the groundwater pH could decline, potentially increasing the mobility of heavy metals and risk to the groundwater contact system as well. So with there's been a fracture during mining in 2018. There was a fracture where we had an inflow event of water into the pit. So the flooding began in 2018 with the water having risen to 1.7 meters. And September 2019, the water level keeps rising with 23 meters in the pit. And they tried dewatering the pit as well, but we have quite a high the water just keeps rising. The water keeps the pit keeps flooding. So an image of that is what the pit now looks like, with the elevated 23 meters since 2019. So 2026, they are still progressively trying to dewater the pit as well. So not another finding quite interesting was the finding of nitrate in one of the farmhouse boreholes as well. So the farm in the surroundings were found to be having some nitrate in that. And so the nitrate concentrations at the mine are proximal boreholes are generally low. So we don't have borehole 1, borehole 6. Those are quite low, but we do have the farmhouse, which recorded alarming nitrate concentrations increasing progressively. So we see it increased from about 1.8 milligrams per liter to 38, and then a straight shoot up to 73 milligrams in June 2019, which is nearly 6.5 times of the WHO guideline. So this could be due to probably fertilizers that the farmers are using to on their land, on farming land, and so it has impacted the borehole quality of that specific borehole. Yeah. So for the groundwater quality index on the highlighted boreholes, so we have the background boreholes, which are also used for which is quite the most potable used boreholes. They are all in good conditions, and we have borehole 2D West and borehole 6, which is the classification, the quality of the groundwater is, or the borehole is quite fair. And then we have borehole 5 and farmhouse 1 and borehole 7. So borehole 5, which is in the mine proximal, has a poor classification, poor quality index, and the farmhouse 1 as well, just due to agricultural activities going on. And then we have borehole 7 that is doing very poor. There is potential or probably some contamination there, as we saw on the sulfates findings that we have had there. So what is the hydrological state of the aquifer? The water table is recovering post-closure. So we have borehole 1, which was the most drawn and has, because that is the borehole that the mine uses as their potable water. And they have used up about 36 to 43 meters. We can see that what was used up has been recovered, and not what has been used, but the borehole is recovering compared to what it was during mining activities. So there's also been a high rise of 11 meter in 1 month of the in borehole 1, which could indicate a gas conduit recharge conduit, and that the dual porosity aquifer behavior around that borehole as well. Borehole 7, that is also in the mine proximal, has had about 28 meters recoveries since mine closure as well. So there is an indication that it is the boreholes or the aquifer is reviving. So how is this a complex system in terms of what our theme is for this webinar? So the groundwater levels had declined approximately by 28 meters at borehole 1 during the mining, but the monitoring data also indicate recovery following mine closure, indicating that the aquifer is quite resilient to recovery. So the water quality, we have elevated sulfates and nitrates from the agricultural farmlands that and also the sulfates from the ore, the type of ore that we have, where we have the the chalcopyrite that is easily oxidized and acidifies the water around it. So the concentrations indicate multiple influence on the quality of the study area as well. So the study area is characterized by a complex karst aquifer system with multiple aquifer units, structural controls, and diverse land uses that collectively influence the groundwater flow quality. So the next steps of the research include sampling of the mine pit lake to study the hydrochemistry, since the hydrochemistry is unknown, and also to conduct post-closure hydrochemical analysis. So in what state is the boreholes right now, the aquifer right now, and also field sampling for the dry and wet season to study how the full ion suite is, and also for the to see what the stability of the isotopes are, and then also do a post closure water balance for chloride, using a chloride mass balance recharge estimation and numerical flow model to confirm abstraction sustainability as well. And so okay, and to the key takeaways from here is that mining in karst aquifers does influence hydrochemical states of karst aquifers, and that this shows us that the aquifer, that Chudi aquifer, is not uniformly contaminated. These background sites remain safe for domestic use, and that the mining pit lake is the critical unknown here. And since there's a direct hydraulic contact with the aquifer, it's very vital, very important to study what is in the water in the pit. Also, karst vulnerability is real, so episodic turbidity spikes confirm rapid poorly filtered surface to aquifer pathways, and also post-closure recovery is underway. So with the rising water, you saw what are the rising water levels and what chemical remediation dictates, what are the long term effects and what the hydrological state of the aquifer remains. So thank you on that. That's all I had on my side.
Thank you very much, Diana, for your very, very good presentation. It's interesting. As you are presenting, I was just wondering if we have data pre-mining, because now we have like during mining and then after mining. It would be interesting to see like on both aspects, on both the influence of the irrigation in the area as well as the mining. That would be really interesting. Because now we know what the mining impacts were, but we don't know like before the mining, how was it, you know?
Yes, yeah. As I'm busy doing my research, I get more curious and getting to know all this as well, just as you've mentioned.
All right. Thank you so much, Diana. I think we will now move into our Q&A session. I hope we still have all our speakers on the call. And I think this is really the first time where we've reached Q&A in record time. So very, very big round of applause to our speakers today. Clearly, they are used to presentations, given the academic background and mining background. I guess you guys are really, really good at keeping on time. So thank you very much to our speakers for really, really sticking to time. So now we'll move to our Q&A session. And if we have any questions, you can just raise your hand and I'll give you an opportunity to ask your question. Just mention your name and who your question is directed to at the beginning of your question so that the person listens attentively to your question. So you have to introduce yourself. Then you mention that, okay, this question is directed to Diana, or this is directed to Dr. Josephina. Then you state your question and also make sure that the question is concise and really straight to the point. Thank you very much. Let me see if we have some hands. And I will also check in the chat box if we do have some questions, and we can see how many we can cover during the remaining time. All right, Darlington, you can give your question. Darlington, I see your hand is up. All right, while we are waiting for, all right, yes, I can hear you.
I have a question. I'm going to allow me.
Sorry?
I have a question for each speaker. So is it okay if I can go ahead?
Okay. Okay. Maybe we can give it like we give the first speaker to answer, and then you can ask your second question so that we move like that. So you can start with your first question.
Just wanted to find out from the study.
I cannot hear you well. Maybe just increase the your volume.
Okay. Can you hear me?
Yes.
Okay. Yeah. So my first question is directed to Professor Kawawa, and I just wanted to find out from one of the slides I saw where he showed us the test hole that had been drilled in order to collect the samples. So I just wanted to find out from the Zambezi catchment, the studies that have been done with respect to salinity. What is the deepest test hole that has been drilled?
Okay, that's a very brief question. Okay, I think you can ask all the other questions as well. Okay, what's the next question? Darlington, what's the next question?
Okay, so the next question is directed to Dr. Hamtoko. Of course, I saw on one of the slides where he showed us the map of Namibia, and she stated that with respect to isotope hydrology, almost the entire country has been studied with using that methodology. So I just wanted to find out, in terms of percentage, what is the extent that the country has been covered, and also in what period have those studies been done. Then the last question is directed to Ms. Diana. I saw that from her presentation, there are a number of boreholes from which the samples were collected. So I just wanted to understand the distribution of these boreholes. Though I stand to be corrected, I expected to see a map in the presentation which is showing the distribution of these boreholes and how wide apart they are. Thank you.
Thank you very much, Darlington. Very good questions. I will hand over to our presenters. I will start with Prof. Kawawa. Your question is, what is the depth or the depth of the deepest borehole?
Very much, Darlington, for the question. So, assessments that are to do with water are not like mining based type of assessments. For mining, you probably find, if you went, for example, in the Zambian Copper Belt, you find drilling done, up to 2 kilometers plus in terms of investigation. But in the Zambezi Basin, our evaluation shows that the deepest drilling has been done actually within the Capriv region in Namibia, where there was an initial BGR investigation done there. And when we looked at the borehole logs and some of the borehole geophysics work, it went around about 250, 260 or so. You bear in mind that it's common in Namibia, for example, to drill, at those depths for water, type of investigations. In Zambia, that's unknown. At the deepest level, you'd be going to around 100, 150 at the most. So I think from our records and from what we know, that's sort of the range that you'd be looking at at the deepest well. Of course, that is a limitation to really fine-tune what the geophysics is telling us. But we're looking into maybe finding some funding that will allow us to do a relatively deep borehole to then confirm our hydrogeological understanding of the area. Thank you.
Thank you very much, Prof. I would also like to ask our presenters, we have a lot of questions in the chat. If our presenters can also just check the chat and maybe just answer some of the questions they are able to answer in the chat in case we don't have enough time. Okay, we'll move on to Dr. Hamutoko. Your question was with regards to the extent of what percentage, when you mentioned that a lot of the area has been covered, what is the percentage or the extent of the study? And I would also like to add a bit to that question, like, has it been harmonized? Have similar papers been harmonized to try and see an overall big picture? Dr. Hamutoko?
All right, thank you for the question, Mr. Darlington. So a systematic review needs to be conducted for us to be able to give numbers. That has not been done Currently, I just looked at an overview of just a general overview, but for you to give numbers, you need to do a systematic review. And I'm looking for somebody, whoever wants to join me on that, you are more than welcome. But also just to highlight, I think my point when I showed the map, it's not to say all the areas have been covered, but I'm saying if we look into most of the basins, there has been a study that has used isotopes. Not all of them, but most of the basin, at least there has been. And of course, these studies are usually not covering the whole basin. It's parts of basin and whatever. But it's just to highlight the growth in which the use of isotope has been in the recent years. And this is actually for Namibia, since the acquisition of that equipment, that we're able to do analysis in the country, and that's why there has also been that increase in the usage. There is also a question on the chat from, I will say the first name because the second name is challenging, Abasa, asking whether we have been able to integrate isotopes into groundwater flow models such as ModFlow. I personally have not done that, but there are people that are doing that. And especially, I know my colleagues at Stellenbosch, they are doing that. They are using isotope in redefining conceptual model, but also into models themselves. I don't know the specific software, but if you are looking for those contacts, I can always link you up to one of the guys that are into those, into using isotope as a tool for validation for model. Thank you.
All right. Thank you, Doctor. And the last question was dedicated to Diana with regards to the distribution of the boreholes.
Yes, I did not have a map for my presentation, but I do have the map in the thesis paper. So the distribution of the boreholes is up gradient and down gradient relative to the mine. So it's the proximity, but the study includes the farms, the household boreholes in the whole surrounding area, not just that around the mine as well. And I see there was also a question in the chat. Sorry to the name from Bertram, if I'm saying the name right. He asked if the mine is factually closed or it's under care and maintenance. The mine is under care and maintenance. There is no mining operation. So the closure that we're speaking of is just the mining operations. There's no mining happening currently. So yes. And Marcus Hetela asked if there is if I used the World Health Organization guideline only, but I used both. But I used both for my study, but only reported according to the World Health Organization guidelines. Is there any? Let me see. Oh, also on the nitrate, Mr. Abbas. So with the nitrate studies, I think this is more for suggestion than I think a question it is. But yes, with now that is based on all data that I've presented, like I said, but we are going to do sampling and study the wet and dry seasons to see what the nitrate effects are within both studies. Could it be, like you said, is it a flow from runoffs, or it's what is the cause of the impact, to look deep into the root cause of it all. Lawrence Ndere, my question is, sorry, he was saying his network is bad. I might have missed some information. Do we have data before? No, we do not have data before the mining operations, because another gap of the study here is there isn't quite a lot of study that has been done on that Tsudi compartment aquifer. So it is a challenge to get data as well. Veronica Kala, to Diana, is there a possibility of continuous interaction between the residual ore minerals in the pit? Yes, which is why there could be possible interaction, but like I said in my key takeaways, we do not have the characteristics of the mine pit water is unknown. So studies are going to be done on that and see what is the state, chemical state and hydrogeological state of the mine pit water. Yeah, I think I've answered most of the questions, and hopefully I have answered everybody's question.
Thank you very much, Diana. We have another hand here. Emmanuel, please pose your question. Emmanuel.
Yes, hello.
Yes, we can hear you.
Yeah, you can hear me, right?
Yes.
Okay, my question is directed to Professor Kawabanda. So I'm asking this in the academic point of view. So I'm a researcher myself on water salinity. So when he was presenting, he was showing us some of the data tools which he was using during his research. Some of them are quite challenging to us students to find them. He was using some drones and the likes, you know them. So I'm asking, is that how can we access his data? I assume someone wants to do a research in a particular area or in that particular area. So how can we, students who have some challenges in accessing the drones, how can we access his data so that we can use them either for publications or for any other research on water salinity? Thank you.
Thank you very much for your question. Prof?
I think it depends which aspect you are really looking at in your research. The drone-based data set is not yet published. This is still, new data that we've just collected. And what we're hoping for is that through SADC-GMI, we could, start uploading some of this information so that it becomes available to people like yourselves for research. If you're looking at water quality data, at least from the work that we've done, most of it you could get it from the journal system. I personally upload most of my papers on ResearchGate, so you can always download those papers, and then they're also linked to open access repositories if you want the data. So feel free to reach out if you've got very specific data needs that you've seen from any of the work presented, then I'll be happy to share with you. Thank you.
Okay, thank you very much.
Okay, thank you very much to our presenters and to all our participants that have asked their questions. We have come to the end of our webinar. Unless there's someone with a pressing question that has not been addressed in the chat, we can give one more person a chance.
There's one in the chat here.
Okay, let me read the one. This one is addressed to Diana. Diana, in the absence of baseline information, it is advised. So this question is from Esther Gustavo. In the absence of baseline information, it is advised not to conclude that the changes in G water, I'm assuming it's groundwater, are due to mining impact. Just a caution there. It is likely, but not definitive in the absence of pre-mining. Maybe an opportunity to use isotope relevant to agriculture or to definitely determine the changes in groundwater quality. I think that's actually a comment. All right, and then we have Nathan's hand. Nathan?
Hey, Getty.
Hi, Nathan. What's your question?
My question is directed to Prof. From from a public health angle, how's the prevalence of high blood pressure and hypertension in this area? I don't know if that's an aspect that you're considering or you considered in this research, considering that I think you spoke of salinity concentrations of around 25,000 microsiemens per centimeter, and predominantly sodium chloride. And this is coming from the understanding that a prolonged exposure in terms of consumption of sodium does increase the risk of such public health concerns. So I don't know if that's an angle that you're also considering in the research.
Thank you, Nathan, for your questions. Your question, Prof. Kawawa?
Yeah, thank you, Nathan. Yes, the issue of high blood pressure has been raised before by the community members. In fact, some of the issues we've not directly been investigating them, but this is informally that we've been looking at in terms of when we run these sort of workshops and community engagements. Three aspects that, at least from the World Health Organization, have been raised. One is around high blood pressure. The second one is around damage to the kidneys. The other one is just increased risk of cardiovascular type of diseases as one of the issues that really comes from consuming high amounts of salinity. However, we have, at least from the people that we've spoken with, we've not recorded real evidence of this in the area. In fact, I'll also tell you that in other places, like if you go to the Middle East and all, where you get high salinity, it also occurs with elements like arsenic. Again, this we've not observed in our investigation. So I guess we are dealing with people with high tolerance levels of how much salinity that they can take. If you really go there, you also notice a very sad scenario where people are cooking in shima, or what some people call it maize meal or pap. When they mix it with this saline water, it looks yellow. Okay, so you can really imagine the state of that environment. So I think, in short, Nathan, no, we've not observed this from our investigations. Thank you.
All right. Thank you very much, Prof. And that, colleagues, brings us to the end of our webinar. I know that it has been an engaging one, very, very good, actually excellent presentations from our presenters. And once again, I would like to thank our distinguished speakers for a job well done, excellent job, actually. And I would also like to thank our participants, the young professionals. Like I always say, without young professionals, there won't be this webinars. So thank you very much for joining. And I would also like to thank Tokozani, who is in the background, making sure everything is running smoothly, as well as the entire SADC team for the platform. And for the questions, everybody that has put up the questions in the chat, as well as verbally asked their questions, thank you very much. And as emerging leaders in the water sector, we all have a responsibility to contribute towards groundwater management. And I know the professor, as well as Dr. Josephine, have identified and mentioned possible gaps that we can align our research so that we can fill those gaps and improve our knowledge on groundwater management. So we hope today's webinar has provided valuable knowledge, inspiration, and motivation for continued engagement and collaboration among our young professionals as well as our experts. Thank you once again for joining us today. We wish you a wonderful evening, and stay safe, stay connected. And as I always quote Engineer James' words to our young professionals, continue flying the SADC flag high. Until next time, goodbye.
Thank you. Bye.
Thank
Bye.
you. Bye.
Thank you. Bye. So,
QTK.
so I'm gonna leave my laptop here in the office so that this thing can download. Then,
Okay.
yeah.
Okay.
Anyway, I'm not planning to work when I get home. It's late anyway.
Yeah, man.
It's late
Oh.
anyway. Yeah.
Yeah, no, thanks, TK. I still have to respond to your emails, but yeah, guys, you'll find them tomorrow.
Nah, don't worry.
Find your
I've done
answers
almost
tomorrow.
everything. I just wanted to check if everything is according to, like, I mean, just check, cross the T's and, just to make
Dot
sure,
the I's.
and dot the I's, just to make sure that, like, I mean, we're aligned. But I believe that all is in order. Yeah.
Okay, all right.
Mm.
All right then. Thanks and have a good evening.
Sure, bye-bye. Some people don't want to leave
They
the
want to
platform.
listen to the conversation.
Hey, colleagues,
We'll call them out.
the webinar is over. Let me just, yeah.
All right, TK.
We'll talk tomorrow.
Bye.
Mm.